If you ask anyone what is faster, a for or a for each loop, you'll get an immediate answer. Of course it's the for loop. But is it? Can the data structure or maybe the size of the collection affect the results? Let's find out. Oh, by the way, and if you think you know the answer, stick around till the end. I'll try to take you on an interesting roller coaster ride. To measure the performance, I'm going to use the benchmark.net library. If you're not familiar with this framework, I suggest taking a look at my previous video where I explain in detail what it is and how to use it. I already have the setup for running this code, so all I need to do now is implement the benchmark itself. I'll define a read-only array of ints that's going to be populated with numbers from 0 to 10,000. Next, I'll create a method for each benchmark. First, a for loop. Nothing special here. I'm declaring a sum variable, iterating over the array with a for loop, and adding the value at the current index to the sum. Lastly, I return the sum. Now I'll do the same for the for each loop. I have a sum variable, the iteration via the for each loop, the value addition, and the return statement. Lastly, I'll mark both of those methods as benchmarks. And I'll go ahead and add the orderer attribute to the class. This attribute specifies how to order the results. In my case, I want it ordered from the fastest to the slowest. Let's wait for the execution to finish. And surprise, surprise! For each outperformed the for loop. You know what? Maybe the collection is too small and there's some minimal overhead in the for loop that's making it perform worse than for each with this sample size. Well, let's test that theory. Benchmark.net supplies us with a nice way of running the benchmarks with different parameters. I'll start by creating a public variable that will hold the collection size. And now for the trick. I can place the params attribute on top of it and provide different parameters. Let's start with 10,000 and maybe 100,000. Now every benchmark method will be measured according to the number of parameters inside the params attribute. In our case, 2. But the benchmarks don't know anything about this variable. Let's fix it. The array variable can no longer be read-only, because I want it to change based on the collection size. Also, I shouldn't initialize it from the start. I can create a setup method that will run before each benchmark. And I'm doing this by placing the global setup attribute on top of any method I want. Now I'll just move the array initialization here and replace the hard-coded value with the collection size variable. I also want to improve the readability of the results. By using the group benchmarks by attribute, I can tell benchmark.net to group the results by parameters. Now let's run it and look at the results. As you can see, the results are grouped by the collection size. So what do we have here? The for each loop is faster again? And take a look, the difference in speed has scaled. It's no longer 1 microsecond, it's 10. Let's add more test cases and run the benchmark one more time. You can see that neither the 1 million nor the 10 million elements has made any difference. For each is still faster. If this is so, how come everyone you ask will tell you that the situation is completely different? Why does everyone think that the for loop is faster? Well, there are a couple of reasons. First, the loop itself is actually faster when using for. But in this particular scenario, we're iterating over objects, meaning we're doing at least 2 tasks, repetition and item access. In this scenario, we're calculating the sum of all items in the array. But we know that each element in the array actually goes from 0 to a specific number, and it's ordered. So in this highly unrealistic scenario, we can replace the index access with the I variable and the logic will remain the same. This loop will be much faster. On the other hand, if we need to access the same element multiple times and we don't cache the element, the loop will be slower. I'll create 2 more benchmarks. First, I'll duplicate the regular for loop benchmark and copy the addition inside the loop. And I'll do the same for the for each benchmark. I also want to show the performance difference if we'll cache the item inside the for loop. Another optimization we can do is in the loop signature. The way a for loop works, it's accessing the array length for every item, which brings some overhead. Since it's a struct, every time we're accessing it, we're copying the value. And while the copy is in stack memory, which is really fast, when we do it enough times, it adds up. There is also another overhead there. If we'll take a look at how the length property is implemented, you'll see that we have casting, pointer dereference, and potentially a null check internally. It all adds up. So what we can do, we can cache the size of the array before the loop. Let's run it again and see the results. And this one will take a while. On a small collection size, we can see that the difference between a Foreach loop and a for loop without index access is so small that I wouldn't count it towards a win for any implementation. Then it's followed by a for loop with a cached length, and then a regular for loop. Take a look at the difference between those two. And I remind you, we're still on the smaller array. Now let's look at the difference with multiple accesses. As expected, the non-cached for loop version is the slowest, but it isn't twice as slow as you might expect, just a fraction slower. The reason for that is CPU cache. The picture starts to change when we look at even bigger collections. Here, the for loop with cached length is faster than Foreach by a nice margin, and the bigger the collection, the bigger this margin is. Confusing? Well, let's dig deeper. In order to understand what happens here, we need to look at how the compiler treats our code. I'll delete all the benchmarks except for the basic for and for each ones to reduce clutter. Now I need to compile the project, and then we can view the IL or the low-level C# code. First, take a look at the for loop benchmark. Except for stripping the curly braces and turning the post-increment operator into a pre-increment, nothing has changed here. It's the same for loop. What about the for each loop? Now this is interesting. For each is a syntactic sugar, and when we're working with arrays, the compiler converts it into a for loop. But it doesn't explain why one for loop is faster than the other. The answer is right before our eyes. If we look closely, between the two implementations we have two differences. The first one is a local alias for a class-level field, and the second one is caching the array element in a local variable. Caching the array element does nothing. If anything, it should slow down the execution a bit, but in all my tests, it didn't. The interesting bit is the first difference, the local alias. This is what actually makes a difference. Take a look at the array access in the for loop. The access happens through the this keyword, meaning it's a field access. While this looks trivial, I mean, we're accessing a reference. What difference does it make which reference we're accessing? By not writing an alias, we're preventing the compiler from doing important optimizations. Basically, when we're accessing a field, the compiler can't be sure that the field won't change. And I'm not talking about the content of the array. I'm talking about the field itself. Another array can be assigned there, or even a null. This forces the compiler to add safety checks. When we're copying the reference to a local variable, the compiler can omit those safety checks because now it's sure that the reference won't change. Let's implement an optimized for loop with all we've learned so far. In this method, I'll add an alias for the array and cache the length. Now, let's run it. You can see that the performance of the for each loop is the same as our optimized for loop, because they're actually the same. And yeah, sometimes in this benchmark you might see the for each loop performing better. The thing is, the difference is so negligible, it's just within the margin of error. I mean, we're talking about fractions of a microsecond. But this doesn't explain why most people think the for loop is faster. Think of it. By now, we had to work extra to bridge the gap between the two. And now they perform the same. So how come people still think the for loop is faster? So far, we've been talking about arrays. But what about other collections? What I have here is the same benchmarks we just did. But instead of an array, I'm using a list. Let's take a look at what the low-level C# code looks like here. When using a collection that is not an array, for each is converted into a while loop. And you can already see how much overhead it brings with it. The try finally blocks, the enumerator reference, the move next invocation, the current property access, the enumerator disposal. Are you curious to see the results? I mean, do you? Really? And here's another surprise. They're actually kind of funky. With all the overhead I've mentioned earlier, you would expect the Foreach version to perform significantly worse than a for loop. But just take a look at that. There's barely a difference between Foreach and an optimized for loop. How so? Well, I'm kind of cheating here. The thing is, I'm using .NET 8. And in .NET 8, there are a couple of optimizations that were made to the compilation process that level the playing field between for and Foreach loops. Thankfully, I've pre-configured a build profile to run on .NET 7. Want to run it and see what's changed? And just take a look at that. Even the non-optimized for loop is almost twice as fast as Foreach. Unfortunately, in Unity, we don't yet have access to this level of optimizations. So our in-game results will be much closer to what we see in .NET 7. The point of this video wasn't just comparing for and Foreach loops. It was to show you that there is no single truth when it comes to optimizations. Different data types, use cases, and frameworks all affect the results. Whether you're new to optimization or experienced, remember not to get stuck with knowledge from years ago. Keep maintaining it because when Unity catches up to the latest .NET features, many of today's assumptions will be outdated. I'll leave a link to the code in the description, and if you like this video, hit like and subscribe. Keep on creating, and I'll see you in the next one.